of the calendar, today was quiz number 2, and what's happening on Monday? Project quiz. Project is due on Monday. Also on Monday, what's happening? Project is assigned. Now I've actually put the project number 3 on your tables. You can just ignore it until Monday if you wish, but I know some folks are finishing up project number 2, so I just figured I'd give it to you before the weekend, help keep you off the streets. So project number 3 is due a week after, so I guess that's the Monday, or maybe the Wednesday because there's a holiday. You'll notice that we are in the middle of this group of 4 classes. What's the common word in all 4 of those classes? Logarithms. So right now we're in the midst of like a mini section, a week and a half on logarithms. Thank you. So last time we looked at logs and their properties. Today we'll look at logs and models, i.e. word problems. And then next class is about log functions, and then we finish up with log scales. And also the test is going to be on the first 10 days of stuff. And right now we're on day number 7. So we're 7 out of 10 days into the material for the first test, which is coming up on the 24th. Any questions on the calendar? Okay. So I think that's that. Let's go to page 30. And again, it says project 3 assigned, sort of, not officially, but if you want to get a jump start on it, make sure you grab a copy. And down at the bottom, we'll go to number 1. And can we start with Jacob? Okay, thank you. Let's take a look at some examples on the next page. We'll go to Todd. Okay, you notice that these 2 functions, they're both exponential because the t is up in the power, but they look different. The one of them is of the form ae to the kt, which is like pert, and the other one is of the form a times b to the t. And so you get different information by looking at the 2 different forms. So I'm asking you 2 questions: continuous growth rate, effective growth rate. One of those questions is easy for each of these problems. Which one is easy to grab from the first example? The continuous, because the continuous growth rate is defined to be that number up there that I called k. So what is the continuous growth rate? It is negative 0.05 or negative 5%. The continuous growth rate for that example is negative 5%. The effective rate is easy for the other one. Effective rate says, what are you basically gaining each year? 1.065. How much of that is the interest rate? Is the 0.065, right? We know that the interest rate always is this 1 plus r. So subtract 1 from that number, and you get that the effective rate is a 0.065 or 6.5%. Okay? Yes, Hassane. If I'm not explicit, you can give me either one. Okay, now we got to answer the tougher questions, because we've answered the natural things. You can just grab that information. But if you want to find, for example, for this first function, if you want to find the effective interest rate, you really want this e to not be here. You want it to look like a 1 point something. So how do we do it? Well, let's see. I know that this 12 is the a, and I know that that t is the same as that t up there. So really what I'm interested in is this e to the negative 0.05 is supposed to be like this 1.065. This is my b. This is what I'm after here. Maybe Maybe I can do this a different way. Pretend that we have these two things up in red are equal to each other, right? They both represent exactly the same thing, just different letters for different values for K and B. What's the same in both? The A's. So divide both sides by A and they go away. What else is the same in both? The T. Raise both sides to the 1 over T and they go away. So really what's equal? E to the K is the same as B. If you want to find B, it's really just E to the K. I have K. It's this negative 0.05. So how much is B? It's E to the negative 0.05. So this is just a matter of typing that into the calculator. Can somebody do that for us? Thank you. So E to the minus 0.05, 0.9512. Okay, so the times 100 is what Tassadé had asked about, and if I'm not clear, you don't need to times 100, but the subtracting one is important. Yeah. So what's the effective rate? What's really happening here? Well, we're ending up with 95% of what we used to have. So what's really happening is we must be losing 5%, which is about right. That's what the purple said. But let's get the a more exact answer. So we're doing this in blue. So that means that the effective rate must be 0.9512, and then, as Garrett points out, subtract the 1. So negative 0.0488. So when all is said and done at the end of the year, basically you've lost 4.88%. Are there questions on this? I feel like there are questions, but nobody's saying anything. We're going to get there. Yeah.
It's interesting that when it's compounding continuously, it causes you to lose less money.
Yes. This is interesting. Maybe we didn't recognize that this looks different from what we saw in earlier examples. If I said that you're gaining interest at 5% continuously, say it again, you are gaining interest at 5% continuously, are you effectively getting more or less than 5%? You're getting more because you're getting it continuously. But this seems to be going the opposite direction, doesn't it? We said the continuous rate was a negative 5%, but in effect, that ends up being not as big of a loss as 5%, when all is said and done. That is curious. Correct. Can you say that again? That was beautiful.
So each time you lose 5%, the next time you lose money, you're losing less because your principal was like.
Yes, that's exactly what's happening. Any other thoughts or questions on this one? Okay. So then going the other direction now for part B. What are we trying to find in part B? The continuous rate. So how do we find the continuous rate? Well, what letter have we been calling the continuous rate? No. The continuous rate is what letter? It's the K. So the continuous rate is supposed to be this K, and I'm still looking at this same kind of, e to the K times B business, and I'm trying to find K. So let's write that equation. I'll do this here in purple. Okay, so my B I know is this 1.065. It's the same B we had from before, and I'm supposed to make it equal e to the K. I'm supposed to find the K that makes that true. So how do you solve this for K? ln. So ln of both sides. 1.065 is supposed to be K. And we're going to type that in, but before we do, we should have some intuition about what we're going to get. The effective rate was 6.5%. The continuous rate, is it higher than 6.5%? Is it lower? Can you guys give me a thumbs up or thumbs down? Is the continuous rate going to be higher than 6.5% or lower than 6.5%. I want more thumbs. Okay, now I want you guys to talk to your neighbors because about half of you are saying up and half of you are saying down. Is the continuous rate going to be higher or lower if the effective rate is 6.5%? Okay, so what did we, have we come to more of a consensus? Is the continuous rate more or less than 6.5%? It's less. This is not counter to what Garrett had said before. What Garrett had said is that normally, if you've got this continuous interest rate, then your real rate, your effective rate is higher. So we're looking at the higher number right now, right? So we just got to think about it from the right perspective. So if you type that in, you should get, something a little bit less than 0.065. What is it? 0.062. 6.2. Am I rounding that correctly, or is it 6.3? 6.3. So about 6.3% is the continuous rate. Okay. So I just brought the thinker out, but I didn't realize this was the first appearance of the thinker. So anybody know who made this sculpture? Rodin. No, this one was made in China. Yeah, but Rodin made the original one, and represents, the culmination of human thought and creativity and all that stuff that distinguishes us from other animals. And so when somebody has a very thinker-worthy contribution, we bring out the thinker. So thank you for your contribution. Okay, number 2, doubling time, and we are up to Bryce.
Oh, for number 3.
Number 2.
For any type of exponential growth model, what does the rate be?
Okay, can somebody tell us?
Twice as much as you start.
Everybody hear Ernie? Again?
How long it takes for you to get twice as much as what you start with. Twice as much as the principal.
Yes. How long it takes for you to get twice as much as you started with. So let's take a look at number 3. I'm going to go to Stephen. Okay, so let's first think about the formula. What's the principal in that formula? $1,000. What's the interest rate? 6%. Is that continuous compounding? No. Is that monthly compounding? That's yearly compounding. That's what that formula is telling me. Super. So I want to know how long it takes the money to double. So then if I want it to double, then how much money will I have? 2,000. So then we write the equation with the 2,000 equals. So can you guys in your groups do some algebra to solve for t, and then try answering part B. And so if I want to solve this equation for t, I know because the t is in the exponent, we're taking logs at some point. But it's too early to take logs right now because there's this 1,000 in the way. So we divide both sides by 1,000, and we get 2 equals 1.06 to the t. So get that 1,000 out of the way by dividing. Then we take a log of both sides. And the reason we do that is where can you move that power? We can put it to the front. That's our nice property of logs. Powers go in the front. And then the last thing is to divide by log 1.06. Yeah, exactly. Okay, so did we got around 11.9 years for the first answer? For the quadrupling, how long did that take? 23.8 years. Okay, so it takes however long to double, and then it takes exactly the same amount of time to double again. And if this is the first time you're seeing this, it should be somewhat surprising. But this is true for exponential functions. However long it takes to double the first time, that's how long it takes to double any time. That's true. The effect is is bigger if you have more to start with. But the amount of time it takes to double is constant, no matter where you are in this process. And if I wanted to know how long to octuple, multiply by 8, stick on another 12 years. So it'd be about 36 years. This is true for exponential functions. It's not true for other functions. It's not true for a quadratic. If I'm looking at y equals x squared, and say I start at x equals 1 and y equals 1, and then say I want to double this guy right here. I want to double that to a 2. What number do I need to put into x? Square root of 2. Okay, so then it takes this long, you know, from 1 to square root of 2. That's how long it takes to double. Okay, and then if I want to double again, 4, what number do I put in? Put in a 2. It takes from the square root of 2 to 2 to double. Okay, I don't know exactly what these numbers are, but I can guarantee you that the difference between 1 and square root of 2 is not the same as the difference between square root of 2 and 2. It does not take 11.9 years every time. It takes a different amount every time. And if you played the same game, you went down here in the square root of 8, you get a third number, different from these ones up here. So this idea that it doubles in the same amount of time, it's surprising. But this is something that exponential functions do. Okay, we're at 4, and I think we'll go to Allie. Okay, let's actually use that formula right now. We're going to jump ahead. What did we say the interest rate was for the example we were doing? 6%. So R is 6%. This is the first, and as far as I know, only time you don't write it as 0.06. This is the only formula where you don't convert those percentages into decimals. You just write it as the percentage. How much is 72 divided by 6? 12, which is darn close to what number? Darn close to that 11.9. Yeah, so it's an approximation formula. It's going to tell you roughly how long it takes for money to double if you know the interest rate. And the nice thing about using this 72 over R is that you don't get into any log stuff, and generally you don't even use your calculator. You just do 72 divided by the interest rate. So if the interest rate was instead 10% a year, how long would it take to double? About 7.2 years. You could do it the right way. The right way is using logs. You'll get something darn close to 7.2. So it's a real nice shortcut that some folks use, you know, without a calculator or without doing any of the algebra. Sometimes it's called the rule of 70. If you call it a 70, you change the number just slightly. You know, pretty much divide by something around 70 and you'll get around the right answer. All right, we are going to, what are we going to do? Let's do number 6. I think we're up to Chris.
This question is from art education. Fill in the blank word always, or sometimes, or never, and discuss with a neighbor. For a given interest rate, the doubling time in years of an exponential growth will blank be greater than the value of the interest rate.
Okay, so I want to know, will it always be greater? Will it sometimes be greater? Will it never be greater? This is not an easy question. We're going to spend a couple of minutes just processing. So process and talk with your neighbors. Okay, so let's come back together. I think we had some groups doing some good analysis here. For example, if interest is 6%, then how long does it take to double? Take about 12 years. And so which one is greater in this case? The doubling time. Okay, but then some folks decided to come up with like really high interest rates, like 36%. If the interest rate is 36%, how long does it take for your money to double? It will take you 2 years. Now which one is greater? R is greater. Could be. So it is sometimes greater, right? Depends on what the interest rate is. Okay. Number 7, I think we're up to Kelsey. 7. Thank you. Okay, so half-life is quite similar to doubling time. Doubling time is how long it takes to double. half-life is how long it takes to decay, to get to half. So how long to decay to half as much? All right. You guys know anything about carbon dating? Yep. Has to do with finding what? Yeah, how old something is. Go ahead, Kyle. Yes. Yes. And we use this technique to figure out how old some really old stuff is, right? Because if you have a dinosaur bone, there's a certain percentage of carbon-14 we expect to be in that dinosaur bone when the dinosaur is alive. But as soon as the dinosaur passes away, the carbon-14 starts to disappear. Does it disappear quickly or slowly? It disappears really slowly, which is why there's still some carbon-14 left in that dinosaur bone, millions of years down the road. And so in number 8, it talks about an annual percent decay rate of 0.0121. So we're losing about 1% a year. So will it disappear in 100 years? It won't ever disappear. Exponential functions never get to 0, but losing 1% a year, you're going to have a lot of stuff there for a long time. And so if we want to figure out half-life, we want to know how long does it take for carbon-14 to get cut in half? Okay, let's give it a shot. If I'm given the decay rate, which one of these formulas at the top in red feels better? The E1 or the B1? I'm given the decay rate. What's the only time you get to use the E1? When you see the word continuous. I don't see it, I'm using the other one. All right, so how do I know what B is? Well, you guys know that B is always 1 plus the interest rate, right? Always. That's what B is. It's 1 plus the interest rate. Well, you know the interest rate. It's given. So just have to plug in the 0.01 into the R. So let's try it. So we know we're going to use this A times B to the T. And we also know that B is 1 plus R. 1 plus, how much is R? 0.0121. That's the... Okay, so is this the right answer or no? No. Make sure we go to... Okay, so stick another couple of zeros. Oh, so then I misspoke before. I read it as 1%, but it's not 1%, right? No, it's 0.01%. Really tiny, really slow. There is another mistake, one that I made on purpose in this one. That one I didn't make on purpose. What did I do wrong? Allie? Yes, right? So 1 plus R is a fine formula. This R happens to be a negative number. It is decaying. Okay, so that means that we crunch these together, 0.99, and then what do we have here? Thank you. So that is the B. That's how much stuff remains at the end of every year. 99.9%. What's that? Yeah. So the 8 and the 1 give you... Yeah. Okay, so that is good. And then we're ready to answer the question. The question says, what is half-life? Okay, so I know I get to use this formula right here. I know that whatever I start with, A, I know that B is that crazy number, 0.999879, and T is part of the formula. Everybody see that formula from the top? All right, what are we after? What's the question asking us for? Is the half-life, which is what letter? What letter is half-life? It's the T. T is the half-life, right? How long? Half-life means how long. So we're after T. You got to put something over here. Well, you want it to be half-life. You want to wait until half of the amount of stuff you used to have is still remaining. You used to have A. Now you have half of A. That's how we fill in the blank. Okay, and then we can divide both sides by a. And then how do we solve for t? We got to use logs. Variables up in the power. So let's use ln just for kicks. ln, so then the t comes down, ln of this guy. Okay, somebody with a calculator? 5681. Anybody get either of those? Okay. So using logs should get the same. Did you round something? 0.99, should be 879. Yeah. Okay. So there you go. It takes 5,728 years for the amount of stuff to get cut in half. And if you wait another 5,700 years, it'll get cut in half again, which is why there's still there's still a detectable amount of carbon in that dinosaur bone, because it takes so long for it to go away. Are there questions on that? Okay, so before we move to the next page, I just want to share with you a link before I forget. So you guys know that that I've got the videos that I make every day, including this one. Just to be clear, the one thing that's in Moodle that says click this link to watch the video is only for February 3rd's video. If you want to watch any other date, you need to change the URL. You got to change the date in the URL. I'm not making a new Moodle thing for every class. It always has the same format. If you're not sure what's going on, just log in and it should be clear if you read the directions. But I know that this project number 2, like I said, can be quite tedious if you don't have the right tools. And so I made a video the other day, I think I made it Wednesday afternoon, and it was just me going through some hints about how to tackle project number 2. Now I changed some of the numbers, but it's quite close to the project in its current form. And so, you know, the URL is here. So take a look if you're interested. If you just type that into your browser, the video should pop up. And just to make sure we get it right, it says 108 hints for project 2 on compound interest.wmv. That's the URL. I guess when I was naming it, I wasn't really thinking of you guys typing in a URL. I was naming it for me. That's what it's 108. It's one big word, no spaces, no symbols, nothing. 108 hints for project 2 on compound interest.wmv. That said, right after class today, I'm going to grab my lunch and come back into this room and eat my lunch in here and talk to at least one person and maybe more about stuff that's on the video and this project. So I'm happy to help if you want to stay right after class. Todd. Do you guys understand what Todd says? He says when you decay something, it is continuous. Can you explain why it is continuous when there's decay like this? Can somebody explain?
Because it doesn't wait for a year to pass to say, I'm going to decay.
Yeah.
You gave us the effective rate.
I gave you the effective rate. If I wanted to change it and make it the continuous rate, this number would change just slightly and would be maybe more representative of what's happening. Yeah, it's a good point. I made a realization very recently, just like a few years back, like 5 years ago. I've been playing with exponential functions for a long time now, and I thought that you know, you could only use the PERT formula if it said continuous, and otherwise you have to use this a times b to the t. Well, the fact is you can use either one. It doesn't matter what the phenomenon is. It just might be that one is easier to use at the start than the other. Let me show you something real quick here. You guys remember this one here, right? This 1,000 times 1.065? Okay, so what I want to do is I want to type that onto my calculator and graph it. Okay, so real quick, 1,000 times 1.065, 1,000 times 1.065 to the t. And in terms of the window, let's say we're looking for, how long did it take to double? For about 6, yeah. How long would that take to double? Around 12 years? Okay. So let's go out 12 years. And if we wait 12 years, then the money will double from how much? 1,000 up to 2,000. So roughly going up to 2,000. We'll go by 500s. Okay, so we should see some nice exponential growth type thing, starting at $1,000, ending at around 2,000 about 12 years later, and that's the function, right? Okay, now we're going to go in here. We're going to graph a different function. Same 1,000, but now we're doing e. What was the value that we found for this 1.065? Is that 6.3%, right? That's what you found for k. So if I type in here 0.063, it was actually a 2 something, wasn't it? Anybody happen to remember or wrote it down? 2.5? 297? Okay. And then I put an X right there. Do you know what we're going to see? It's supposed to be exactly the same. That's the point. It's supposed to be exactly the same. I'm going to hit enter over here on the left. It's going to make it a little bit darker, because if you graph the same thing twice, you don't see anything the second time. So if we did this right, it should completely darken the graph that was already up there. And I didn't realize, I just kind of thought that if it's continuous, you're using the PERT. Otherwise, you're using the other one, and you can't mix and match. But you can. All we're doing is converting, right? You just got to, yeah, you just got to figure out what the right rate is, depending on which formula you're using. So Todd is absolutely right. Fossils don't just decide at the end of the year to decay. So it's really a continuous thing. To make it the continuous thing, this number, the 0.012, would just change a little bit.
If we were to have enough time to double check our answers.
You can do both? Absolutely. Good. Okay. Let's we're going to skip 9. Get somebody to read some history stuff. Topher, number 10. Hold on one second. So we're talking about the book about logarithms. So the idea in this case was Napier's invention of logarithms. Go ahead. Keep going. Mm-hmm. Do you guys know Kepler's 3 laws of planetary motion? Anybody name any? Maybe you've heard of them. Can anybody name any of the 3 laws? What is the shape that orbits rotate around the sun? It's an ellipse. That's one law. That ellipse, the planets travel in elliptical orbits with the sun at one focus. Another one said that, yeah, it said that if you, yeah, it's a little bit involved, but if you were to connect, say, planet Earth to the sun right now, and then let us spin around a little bit and then connect us to the sun again, then we've got this like almost triangular shaped region in here. It's curvy on the side, but it's basically a triangle, and that has some area. And right now we're in winter. Do you guys know if we're close to the sun or further from the sun than in the summer? We're actually closer to the sun in winter than we are in the summer. I know it's weird. It has to do with angles. Yeah. But when we go further away from the sun in the summer, we're not traveling at the same rate. Like right now, we're close to the sun, and so the sun's gravity is affecting us, and we are whipping around the sun kind of quick because of the gravitational pull. So we're actually going to start rotating around the sun kind of slower when we get way out here in the summer. But it turns out that if you waited for us to sweep out a triangle over here for like, say, 30 days, and you find the area of that triangular thing, And then you wait for us over here for 30 days. Now we're going to be moving slower out here. So we're not going to cover as much distance, but we are farther. So the triangle is kind of like bigger this way, but shorter another way. It turns out the areas of those two things are the same. If you go 30 days, anytime, it's always the same area. And it's not just for Earth, it's for any planet. Yes? Does Australia have a longer winter? Are they in, what are they in right now? They're in summer right now, right? Yeah, so I mean, everything for us is flipped over for the Southern Hemisphere, so.
Yeah, it's all relative how close they are.
Yeah, yeah. There is a third law from Kepler. Anybody know what it has to do with? So I can't quote the exact formula. I don't remember the powers in the equation, but it has to do with looking at all 8 or 9 planets. I forget about Pluto. But you look at all the planets, you look at how long it takes for the planet to orbit around the sun. We take about 365 days. Further away, they take longer. And you also look at how far the planet is from the sun on average, because it changes. And it turns out there's some quite nice relationship between how far a planet is from the sun and how long it takes to do one complete orbit. So those are Kepler's 3 laws. Now he came up with his 3 laws, not by Googling stuff and doing calculations. He came up with them by looking at tons and tons of data. He had numerical data from somebody else before him looking up at the sky and charting meticulously the position of the planets on every different day and where things were. And we're talking people spending their career, like this was their career, was just collecting all the data. Kepler comes in, he says, I'm trying to analyze this data. It involves massive amounts of calculations, but we don't have the nice tools to do these calculations. Logs come along, and that frees Kepler up to actually do the calculations. He uses logs to help him do the massive calculations that he's been waiting for, and he comes up with these 3 laws that turn out to be quite nice. Todd? Yes. Yeah, so Tycho Brahe is the guy who did the meticulous data collecting. Okay, we're going on to Emily, the invention. Okay, logs were invented kind of out of the blue. That's what this is saying, and that is very unusual in terms of math and science. Math and science discoveries don't just happen in a vacuum. They happen because there are results centuries worth of stuff that happened leading up to something. So calculus is invented like mid-1600s by Isaac Newton and Wilhelm Leibniz. They didn't create everything on their own. They happened to put together the pieces of what had been building for like 200 years. They didn't just start from nothing. They looked at all this stuff. There were a bunch of folks who got really close to calculus. They had little snippets here and there. The guys that invented Newton and Leibniz, the inventors of calculus, they just kind of were able to connect some things that people weren't able to connect before. This is how math and science gets developed. This is not what happened for logs. Nothing foreshadowed the invention of logs. It just came out of no place. This one guy, John Napier, sitting by himself in Scotland, said, hey, what if I do this? And, yes. But the idea of looking at them from the other perspective, from the logarithm side of things, was something that nobody had done before. And coming up with this table and then these properties and being able to use them to solve equations, this is what Napier gave to us. Without a calculator. Okay, we're going to try this group thing. We'll get somebody to read, and then you guys will spend 14 minutes seeing if you can answer this one question. Sam. Yes. Okay, so this is a doubling question. I had my son in the summer, and his birth weight doubled, and I said, hey, if he continues to double, he'll pass me in like a little while, and then it'll just keep going. And I said, well, at some point it'll It'll be more massive than the Earth, so let's give it a shot. Now I realize that perhaps this question is a little bit too precise. On what date? So we'll make it a little bit gentler, and if you answer this question, then you might think about continuing and figuring out exactly when. But how about we say, how old will he be? Right. Right. So that's the kind of detail stuff that I'm trying to omit here. So 5 months out of 12 months in the year, we'll pretend they're all equal months. We'll leave your stuff, but it's a good point. Okay, so some folks have the internet. If you don't have the internet, I typed something in up here. Let me pull it up just a second. Okay, so I did type in mass of the Earth, and this is what I found right up here in Google. So if we want to use that number. Okay, so we need to think about converting. And if you want a conversion thing, you can come up and type it in.
What is it?
This is kilograms.
What is it? 2.2 kilograms.
What are you after? 1 kilogram in pounds.
2.2 pounds.
Anybody need this number? I'm going to.
2.2.
Okay, so we want the other one. 1 pound in kilogram.
Why don't you just look up the mass of the Earth in pounds?
Okay. Mm-hmm.
Or you could just state its weight. You just got to divide it by 2. Someone's born on the 14th of July.
Yes. Oh, is that right? My brother was also on the 15th. Yeah.
Ounces in a pound, right?
That's correct.
Oh,
Right, so I have 280. I did them in ounces. So 280 equals 140 times. So is it growing continuously? Does that mean we're supposed to increase?
Remember how we looked at those two graphs?
Back and forth?
Whatever you choose is fine.
Okay.
Yeah. And so the K is the part you don't know, or what does that say? N?
Yeah.
Yep,
yeah.
fine. And then next to the N, there should be another letter. It's what's?
Right, but it's going to be this 0.41666.
Is that how many years? Is that 5 months? Yes, exactly. You put that right up there. You got it. Yes.
Is that really your kid's name?
Yes.
His initial spell.
Yes, we made a cow.
This math problem when he's older.
I don't know. It depends on how much therapy he's in by that point. Like because Dad does stuff like this.
Don't feel bad. I know this kid that his parents named
Gabe
Gabe Asher.
Asher.
Yeah,
Terrible.
He changed his name. Oh, it's horrible. He changed his name by senior year of high school.
Yeah, I don't blame him. Yeah. Okay, so we're working. So we have this 1.1487. So can you guys talk about that? Okay, how's it coming over here, guys?
I think I've got it.
You have an answer.
I think
Is it that many years?
so.
Okay.
Because what I did was I took what we did here,
Mm-hmm.
and I just put the mass of the Earth,
Mm-hmm.
and then the weight to t, to the power of t.
Mm-hmm.
I figured it would come out to be the same thing because it's basically like
So what did you do where there's a 1.06 here?
I just left it as
1. Just 1?
one. And that's where I'm really kind of at a roadblock.
Yeah, I feel like we need to.
I didn't think that was correct.
Yeah.
But the approach, I think, was
Yeah, so I feel like we need to first pick a formula. So if you want to use the PERT formula, that's okay. If you want to use the a times b to the t formula, that's okay. Do you guys have a preference, or is somebody sort of heading somewhere with one of those formulas?
I think we're going to be doing the 8 times.
Okay, so if we do the a times b to the t, then you got to use the fact that the weight doubles after 5 months. So you can plug in 5 months for t, but we're doing everything in years here. So let's make it 5/12 for t. So t is 5/12. B is something we don't know yet. A is the starting amount. What's the starting weight?
8.75.
Yeah, and so let's do 8.75, converting ounces to pounds. And then if he gets to 5 months old, how much does he weigh then? How much will he weigh after 5 months? 17 and a half. That's the capital A, right? We're saying he will weigh 17 and a half. So capital A is 17.5. And now that we've got an equation, we should be able to do some algebra to find that B. That B is going to be the key.